Alright, right now we are in pre-cal class. That's Nelson. That's our camera recorder. That's Miss Rohan. She up there. She about to teach us. This is Celia. Alba, say hey, Alba.
I'm gonna post this.
Say hey. Hey. We're gonna have a fun day at pre-cal.
Alright, y'all, page 23. We are gonna be cruising for this short lesson.
Say hey. Hey, hey, hey. Say hi, Miss Rohan. Eileen, you ready for today? Yeah, same. I'm not really ready. Make sure to subscribe to us, thumbs it up, and watch our pre-cal class. Okay, so class is about to start, and some of us are late.
It's 29 classes. Starting.
Okay, class is about to start. Let me go sit down.
Here we go. Alright, I'm gonna take attendance. Here we go.
Here we go.
Yeah. So you'll still have lunch, fourth period. So it's like that awkward, like really early morning lunch, alright? So I'm gonna take attendance because it is 29, so class has started. I know the bells are kind of weird. Lay out your notes to page 23 for me because we're gonna jump like in super quick because we got 30 minutes. Huh? What a dream! Okay, great. I forgot fourth period is long on Wednesday, right? Yeah. I last year didn't teach a fourth period, so I didn't get to experience that. Okay. I don't know if that's good news for y'all, but it's great news for me. Okay, that's a good deal. If y'all get going and we get set and we're working hard, then I will honor that and try to still keep it to 30 minutes like my other classes and then give you the time to like ask me questions on the homework and work on the problem set. Okay? Cool? Alright. Angelica. Here. Jonathan. Dennis. Nelson. Here. Gladys. Here. Cecilia. Here. Eileen. Here. Edo. Tanya. Here. Andres. Here. Jacqueline. Here. Alba. Zulema. Here. Jordan. Lovely. Okay, then y'all take a look. We are going to not go through this entire problem, but I want you to take a look at it and just make some observations.
Oh man, I've been trying to leave this class for the past 3 periods and I keep it.
Oh, were you not safe?
Yeah, that's the second period now that I did it.
Do you want to go bring it real quick? Okay, here we go. Wednesday, we jump pretty much straight on in, and I don't do a whole lot of do firsting because we just don't have time. Okay? In your class, we might kind of change it, but I kind of like Nelson's suggestion of using some of the time for like almost like tutorials where you can work on my problem set. I'll have you work on my problem set so you can ask me questions. Okay? All right. So taking a look at this situation right here, this is about, this is a graph showing minimum wages in different years. So you'll probably notice in general that our minimum wage per hour is goes up over time in general. Anyone know what minimum wage is right now? Something like that. I think that's right. Anyone else? No? You think it's $7.25? I think when I was working at Wendy's back in the day in high school, it was like $7 or $6 something like that. So it's gone up a little bit. But anyways, taking a look at this, we're going to kind of skip through some of these first ones. What do you notice in general? So we got a chance for some participation points. Anything you notice about this graph? What's different about this graph? What does it kind of look like? It's kind of going to be related to some of the things we talked about today. What do you think? Okay, so we got these lines that are constant, so it's like, this is maybe like 350, or it looks like a little less, maybe like 325. It's 325 this entire time, it's not changing. Okay, cool. And then it goes somewhere else and it's constant again. Other thoughts? What else do we notice? Other observations? Just take a look at the graph. What do you, anything else you notice about this graph right here? Yeah? Cool. In general, like we said, the minimum wage is going up. The lines are getting higher as the years are going by. Okay. Taking a look at this last one right here that says, do you think this graph is continuous? Why or why not? This is the word that we're going to be talking about today. We're going to be talking about whether a graph is continuous or not. So we haven't learned what that means, but just by looking and giving it your best educated guess, what do y'all think? Let's hear some thoughts. Do you think this graph is continuous, yes or no, and why not, or why do you think so? Yep.
I think no.
Not continuous, okay, why?
Because like these dots at the end, some are shaded.
Okay, so maybe something to do with our like shaded dots and our unshaded dots. Anyone in here also think maybe that it's not continuous? People that were thinking not continuous? Okay, Jacqueline. Okay, you are correct. This is considered a discontinuous graph, all right? And we're gonna learn today what that means. Basically, anytime we have something like this that has breaks and holes and things in our graph is gonna be discontinuous, all right? So let's talk about what that means. Continuity, here we go. All right, so it's right here. The graph of a continuous function. If this would be continuous, it would have no breaks, holes, or gaps. Basically, you can trace a graph of a continuous function without lifting your pencil. So kind of like if that helps you to think about it, here's an example of a continuous graph, because I can, on any part of my graph, I can trace it, and I never have to lift up my pencil the entire time, right? On the last example, I would be coming along, and then at this here, what happens? I like jump up here, and so I have to lift up my pencil to like keep tracing the graph, right? Okay? So that's like a basic way to kind of remember whether something is continuous or not, right? All right, to understand what it means for a function to be continuous from an algebraic perspective, it's hugely helpful to examine the graphs of discontinuous functions. So today we're going to be talking about when a graph is not continuous. That's what we call discontinuous. What are the different types of discontinuity that we might see? Like how we saw the graph at the beginning was discontinuous. Let's talk about some other cases when it also might be discontinuous, okay? These are going to be our three different types, okay? In general, let's use our like tracing pencil test just one more time to confirm that they are discontinuous, and then I'll talk about each one of them. But for example, with this one, if I move from left to right, and I'm trying to trace it, in order to get over to this side over here to trace the entire thing, I would have to like lift up my pencil to come over here, right? So if it has, anyone know what we call like right here, the like imaginary line that's like between these two parts of our graph? Anyone remember? Maybe from back in the day you might have learned. It's called a asymptote. Anyone ever heard of that? You see a couple of people that are like, if not, we're going to talk about asymptotes this year. But if you've heard of that, that's one example of like a type of discontinuity you might see. Okay. Over here on this one, we're tracing, and then whoop, we have to jump up here. We have to pick up our pencil, right? Okay. If it moves from one value to another value, that's another type of discontinuity we're going to talk about. All right, this one, we're tracing, and it pretty much looks like it keeps going, but whenever we have an open circle right here, that means that one point is missing, and so we actually have to like jump over it and then keep going. Okay, so that's another example where we have discontinuity. So let's talk about what these three are called and a little bit more about their definition. Okay, right now we're going to be talking about at a specific point whether it is continuous or not. So I was talking about kind of before whether the whole graph was continuous, whether there were any breaks, holes, or gaps. What we're going to be talking about right now is if I have like a graph that looks like this, then I could be over here at this C value. I don't have to pick up my pencil as I go by C, right? My graph is continuous over here, but over here at this value is where I have a break or hole, so we'd say it's discontinuous at that C value, okay? So examining a point C right here, this is C. We call this type of discontinuity infinite discontinuity because from the left or from the right, it's approaching either positive infinity, see how this is headed towards positive infinity, the y, or the y is headed towards negative infinity. So go ahead and write that down. It approaches negative infinity or positive infinity as x is approaching c from the left and from the right. Cool? Okay. A jump discontinuity. I know it kind of seems like in all of them our pencil jumps somewhere else, but by jump, what I mean is that at C right here, my y value from the left side, let's say it's down here at like negative, I don't know, let's pretend it's down there at -4. And then up here it's at 2. It jumps from one value to another value. So it jumped from -4 all the way up to +2. Okay? So a jump discontinuity says that from the left and from the right, it's approaching two different numbers, basically. Okay? Approaches two different values or two different numbers as x goes to c from the left and from the right. So not infinity. This time we're talking about two different real numbers, real y values. Last but not least, removable. What does it mean to remove something? A little letter? Take away. So like picture yourself coming up to the graph and you literally just like pluck out or take away one little point from your line. Okay? That would be considered a removable discontinuity. It would also be removable if like you even like took out that point and like placed it right here above. It's like a funky looking graph, but maybe right here at C, it doesn't exist right here on a graph, but it's like plopped up there for whatever reason. Like, you know, like our piecewise functions, we've talked about how it can be doing one thing and then change and then do something else, okay? And so this is an example and this is an example of removable discontinuity. And what that means is, notice this time, we're approaching from either side. Let's say this is 5. See how we're approaching the same place, the same y value? However, at that point, it just doesn't exist. Okay, we like plucked out the point at that point. So it approaches the same value as x approaches c from the left and from the right, but then that one point is not there. Yep?
So it will be two different ones, or it's still one?
Interesting, so like you're saying like one graph?
Yeah.
It could be, so it could be like a piecewise type situation, but you're right, it actually still could be one function, like one equation, but maybe at this point we run into one of those issues we talked about, like where, you know, we talked about like we can't have 0 on the bottom, or we can't have the square root of a negative or something like that. So for some reason, this c value, when we plug it into our function, is giving us some sort of not real solution to where that point is like removed. So there's kind of some different cases that we'll look at, but in general, this could be either separate pieces or it could still be one function, but that point is missing for whatever reason. Okay? Cool. All right, great question. Did I give you your stamp for that question? Good. Cool. All right, moving on. Therefore, there's this thing that we call the continuity test. 3 things that we need to check, and if all 3 of them work, then we can say something is continuous. Okay, we're like, okay, that means like I can trace my pencil and it's going to be continuous. If one of these things is not true, then automatically we know it's discontinuous. Like if you check the first one and it doesn't work, you don't even need to check 2 and 3 because it's already discontinuous. It needs all 3. Okay, so let's take a look at what the continuity test looks like. I am going to use I'm going to make this go a little bit like this. Okay. Let's pretend this is my function, and we're talking about this c value over here, okay? First thing is that you need to check that there actually is a value at x equals c, okay? So the first thing you need to make sure is that f of x can be evaluated at c. So in this case, if this is c, we could say that this point actually does exist when x equals c. It's like colored in up here at 3. Okay, so it exists. All right? If that's true, it could be continuous. We got to keep checking some things. Let's keep going. Next, second thing you got to check is that f of x is the same value from the left and the right side of C. We call it like the left-hand approach and the right-hand approach. It means if you look at your graph, tracing it from the left and tracing it from whatever's going on the right, I need to make sure that those two things match up, because that means like with your pencil, you would never have to lift it up if the two sides match, right? So take a look at this one. Here's my left side, here's my right side. Do they match up to the exact same point? This is at like 3 and this, I don't know, maybe it's like down here at 2. Are they going to the same spot? No. So this is an example where like this graph would fail the second step and we would say it's discontinuous, which you can see it's discontinuous there, right? If not, if maybe this like perfectly happened to match up to where the circle was like right on top of it, we would say that it passed that because the left and the right were coming to the same spot. Okay? Cool. Last, number 3. The value of the function that we found right here and the value of the function that we found from the left and the right side approach have to be the same. So basically step 1 and step 2 have to match. The value of the function from step 1 is the same value of the left and the right side approach. So let me show you an example of something that would fail that. I kind of already talked about this example. Okay, let's say I got this funky looking function that's like this, okay? Step 1, can it be evaluated at C? At C, we do have a point. F of C would be 10, right? Okay? Good. Step 1, it passes. Step 2, it's same from the left and from the right. So if we don't actually get to C, but we approach C from the left, it looks like we're headed towards 2, right? Do you agree? From the other side, it also looks like we're headed towards 2. So that's what we say the left and the right side approach. Remember, I'm not saying like actually the point, but I'm saying the approach, I'm getting closer, are going to the same place. They're both going to 2, right? And so it would pass the first one, it would pass the second one. We might be starting to think that it's continuous. However, does the value of number 1, which we said was 10, match our approach, which we said is 2? No. So something's going on here where those are not continuous. And notice right here we see there's like a break or a hole or a gap in our graph. So that failed the third one, so it's discontinuous. Okay? So we got to make sure it exists at the point, the left and the right match, and then third, that's step 1 and that's step 2, where this is talking about the same place on our graph, the same value. Okay? Alright, let's see what this looks like in numbers. Example number 1. We've got a piecewise function, and it says determine whether f of x right here is continuous at, and they have to give us a specific point, a C value, right? At x equals 2. So over there on our graph, we want to see if at 2, we have to lift up our pencil or if we're good to go. Justify using the continuity test. So I went ahead and I just pasted my little test down here. You can keep glancing above at your 3 steps because we need to show all 3 things to be able to say that this is continuous, right? Okay, step 1. Let's see what the value is of our function at 2 and see if it exists. So what we first have to try to find is f of 2 and plug it in, and like maybe we're going to get 0 on the bottom, or maybe we're going to get the square root of a negative and we're going to run into an issue, but maybe we're going to actually have a point, we're going to be fine. So f of 2, based off of what we did when we learned piecewise functions, Zulema, can you tell me whether you would plug in 2 to the first one or the second one? Yeah, how do you know? You're right.
Because it's 2, so it would be like 2.
Perfect. It's got to be with this one that has the equal sign, right? Because this one is all the way up to 2, but then it's going to be like an open circle there, and then this one is going to start at 2 and include 2 on. So we're gonna plug it into this one. So we're gonna say square root of 2 plus 7 minus 2. Go ahead and solve that for me. See what you get. Should be able to do that square root by hand. It's one that you'll know. Andres, you got it? What'd you get? 1 is correct, because this would be root 9 is 3, 3 minus 2 is 1, okay? So that exists, so we basically just passed step 1 of our continuity test. Maybe it's continuous, I don't know, we gotta keep checking, because it has to have all 3. So let's go to number 2. Number 2 says that if I were to basically look at the graph, like conceptually, let's understand what's going on here. This is a piecewise, and notice there's a change at 2, right? It's going from this thing, I don't know what it looks like, but maybe it's like, woo, and it's coming in to 2 somewhere, I don't know where. We're gonna try to find it, that's gonna be the goal. But it's gonna have like an open circle once we get there, because we don't want that point, but we're gonna go up to it, okay? And then on the other side, it's doing something else, woo, and it either is gonna come in right here at the same point, or maybe it's gonna be up here, or maybe it's gonna be down here, I don't know. So the goal is figuring out where both of them are going, all right? So even though this does not have an equals to, what we're gonna do is we're still gonna plug in 2 to that equation to see like what would it have been, what is this value of this open circle if it would be there? Because that's where we're like headed towards, but then we stop, okay? So let's plug in 2 to this one, and we've already plugged in 2 to this one and see if those numbers match up to the same x value. So sorry, I should have drawn this one. Where's this one coming in? It's coming towards, I want to draw this more accurate. I don't know what the heck it's doing, but at 2 it's equal to 1, right? And we want to see if this side matches up. Okay? So let's plug in 2 to the first one. 2 times 2 squared minus 3 times 2 minus 1. Go ahead and solve that for me and see what you get. Solve that for me. And we already plugged in 2 to the second one and got 1, right? So we're going to see if those two things match. Now someone get. Did y'all get 1? 1? Andres got 1. I see him shaking his head. I still need to give you a stamp, right? So Lana, did I give you a stamp? Alright. So, does it pass step 2? So this one happens to be an open circle in the exact same spot as this closed circle is like on top of it. It's kind of weird, right? It's like an open circle, but then the other one starts in the same spot. So technically, if I was tracing, would I ever have to pick up my pencil? No. So far, I'm good because those match. And then third, I just want to check one more time to make sure that the point is not like floating above. Does step 1 and step 2 have the same value? So you can say, good, step 1 and step 2 are both 1. You know, like you don't have to use the same way I'm writing this. You can kind of just say it in your words, but you need to acknowledge that that's true. And then say, therefore, continuous.
So we just plug in X, they're both the same.
Which they won't all be piecewise functions, so we'll talk about that. But essentially, in a piecewise, what you're doing is you're plugging it in to both of them to make sure that on both of those equations we're headed towards that point. Cool? Not that bad, right? Just kind of weird, kind of like conceptual. All right, so that one is an example of a continuous one. I want you to take a look at this next one. We got another piecewise function here that we're trying to figure out whether it's continuous at 0. So notice a lot of times we're checking that point where the graph switches because that could be the spot where it's discontinuous, right? So take a second. I'll kind of walk through this one with you as well in a second, but I want to give you a moment with your neighbor to kind of at least attempt to try to start doing 1, 2, and 3, checking these and seeing what you feel like is going on, and then we'll discuss it together, okay? So give it about 1-2 minutes first trying the continuity test with your neighbor, then we will pick up back together again. Step 1, find the value itself, make sure it exists. So step 1, what did you do? Well, you plugged it into the first one, right? What does step 1 say to do? Step 1, if you were eventually we're gonna have to plug it into both, right? To check both. But for step 1, kind of like Zuliana answered when we did this last one. If I'm plugging in 0 to this function and I'm finding f of 0, which part of my piecewise includes 0? I want you to do this by hand. For right now, let's pretend like we're doing it by hand, because you should be able to do it for right now by hand. So looking right here, is 0 going to be part of, if you look at your piecewise right here, Angelica, is 0 going to be part of this one or this one? First one and the second one. Why? Because 0, I see the equal sign. And so this is all the numbers up to 0, but it doesn't include 0. And then this is the number 0 and on, right? So we're going to plug it in here. And so it's just plugging in 0. And you plug in 0 and you get 0. So that's what 0 is equal to 0. You can plug in your piecewise. But remember how we learned to plug in our piecewise? We'd go over here to the graph. And come up here, you want to kind of do this. Okay, and then you remember how we learned this button? And you can type it in here. And you can say 1 divided by x. Oh my gosh. Did you all need work? Did you lose something? Your piecewise. Divided by x. Right. For x less than 0. Right. This one is x for x greater than or equal to 0, right? Okay. And you press enter. And when you go back over to the graph, you can say f1 of 0 is 0. But see how it was kind of quicker to just like figure out which one it was and plug it in, and maybe actually like plug it in on your calculator. But you can't do it on your calculator. Cool? So that's step 1, is finding the value itself. Cool? Okay. So step 1, did it pass? Yes. F of 0 is 0. Well, let's talk about step 2. On step 2, now, regardless of whether this says equal 0 or not, now we want to plug it into both of them, right? To see the left and the right. So you get 1 over 0 is undefined, and you get 0, right, when you plug it into x. And do these two things match? No. And so we fail step 2. So those are not the same. Therefore, we know this is discontinuous, which is the same thing as not continuous. Okay? But it's important to note here, like, if I ask you to justify using the continuity test, like, you need to show me that you knew step 1 we were good, it was step 2 that was our issue, right? So we gotta understand where the problem was. I did not ask you in that one to tell me which type of discontinuity, right? Remember there were 3? One of them was infinite. Anyone remember any of the others? You can shout them out. Infinite, what else? Jump, and removable. I didn't ask which one it was, so now we're gonna kind of like add that in. We're gonna see if after we figure out something's discontinuous, if we can use the graph and some other tools to figure out which type, like whether it was an asymptote or whether it was just missing or what's going on there, okay? If I graph this piecewise, we know how to put a piecewise into our graph, and we take a look. For the sake of time, since it's a Wednesday, like I'm not gonna have y'all actually graph it, you can just look at my picture, okay? Because we should be able to graph that. Let's take a look here at 0, at what's happening, okay? And you'll notice, you can see that this side, what's happening to our y, we're going down forever towards what? For your x value, we're approaching 0, but what's your y value doing if it's going down, down, down forever? Negative infinity, it's going towards negative infinity, right? And this side right here, we see that it's approaching 0. So that's why this one was undefined and this one was approaching 0. And so our graph is gonna help start, let us see like whether this is gonna be infinite or removable or a jump. And since this is approaching negative infinity, what type of discontinuity do you think it might be? If it's approaching negative infinity, which one did we say is a type of discontinuity? Infinite discontinuity, right? Cool. Okay, so let's take a look at this one and see if we can not only figure out whether it's continuous or not, but figure out what type of discontinuity if it is discontinuous. All right? This one, notice, like Nelson, you were kind of talking about, is not a piecewise. So it's going to be a little bit different if we have to look at like the left and the right side. Okay? So for the sake of time, let's go ahead and actually on this one, it's asking you to do both. So you'd have to do like 2 continuity tests. Okay? But let's just still do one. Let's check at x equals -3 for the sake of time. If on your problem set, it says for x equals this and x equals this, that means it's asking you like almost 2 separate problems. I need 2 continuity tests. Alright? Okay, first one. X equals -3. Here's your function. Step 1 tells us we just need to find f of -3 and see whether that even exists. So go ahead and plug it in on the top and the bottom and see what you get on the top and on the bottom. Putting it on top, 0. Putting it on the bottom. But what happens when you say about 0? Which does that give us 0? You get 0 on the bottom. Division by 0. If you try to put it in your calculator, it's actually 8. So it's not equal to 0. Okay. I plugged it in. I got 0 on the top. I plugged it into the bottom. What did I get on the bottom? 0. It's very tempting to say that that's equal to 0, right? But what did we say if we have division by 0? That's actually undefined. It's not equal to 0. This is undefined, which means from step 1, we already run into an issue and we fail the continuity test. And so we know that this is discontinuous without even needing to go and check the left and check the right. Okay? If you passed that, let's say this was like +9 or something, okay? From the left and from the right, you might be wondering like, what would you do if, since this is not a piecewise and you don't have like 2 things to plug it into, okay? You could start like coming up with numbers that are really close to -3, but are on the left side, like negative, I can't think of anything, 4 point, yeah, you could do -4, but even like really, really close. So negative 4.0, like what's on this side of -3 point, negative 3.00001 or something, right? Is like right after. It's like really close to it, but like right after it, right? So you could start plugging in some values like that to see if those values are approaching the same place. But regardless, then you're going to need to use your calculator, right? And so another strategy is to just graph it on your calculator and like see what's happening on either side. Okay? So I went ahead and I graphed it on my calculator. And let's take a look over here at negative 3. On your calculator, if you guys graph it, it will actually look continuous. I put that little like hole there. Okay? It'll look like a solid line. So it's kind of tricky because it might make you think that it's continuous. But if you type into your trace function, which we're going to go over in a second, you'll see that actually, like if you looked really, really close at the function right here, negative 3, that point is actually missing. You just can't see it because like with all the points there, it's hard to see. The hole's not as big as like when I draw it like this. Okay? But on your graph, you can see that like from the left and from the right now, we are approaching the same value, right? And so the graph can help us to kind of like figure out where we're going, whether we were two different places or whether we're the same, okay? So this is what type of discontinuity. Let's say this is multiple choice, and you know it's not A, which says continuous, but B says infinite discontinuity, C says jump, and D says removable, and you got to figure out which type. Taking a look at what's going on here in the graph, which type, Jordan, which type do you think this would be? Infinite, removable, or jump? Removable. Just one point is like taken out and is undefined at that spot. So this would be removable discontinuity at x equals negative 3. Okay? Say that one more time. Yeah, like in this case, like it also asks you to check 3. Okay, so let's pretend like we did that. If we found 3 and we plugged it in, we would have also gotten 0 over 0. So we would have known that it was discontinuous. But if you go ahead and look over there at positive 3, here's positive 3 over here. At that point, actually it's like right here. At that point, it's not removable discontinuity. Take a look at what's happening on either side of positive 3. Gladys, what do you think at positive 3, which type would it be? Infinite, removable, or jump? Which one is going on that side? Right here. So we said this one's removable, right? Over here at negative 3. Removable at negative 3. But over here at positive 3, now that we're looking at our graph, which type is it? Not quite. Not quite. Good try. Which one do you think, Angelica? Over? Infinite is correct because it's going to negative infinity and positive infinity. Okay? Jump is when it's going to go from like 2 to 5 or something, like it's like 2 different actual values. Whenever it's got the infinities, it's infinite. Yep. So for this one, it's the same graph. I graphed this function, but this one I know we focused on just solving the first one, but it asked you actually about the continuity in 2 different places. And so I'm just talking through both of those examples. This type of continuity is one thing and this one's another thing. But it's discontinuous at both places. At like 2, wherever 2 is, it's continuous. We don't have to pick up our pencil at 2. So like at 2, a whole other thing is going on. Okay? Cool? Alright. So, last one down here, B. I want you to take a look at B and do your little test with your neighbors. I know, oh, sorry, I forgot. Yours is like out of order, right? Yeah. But you're doing good at finding which one we're on, so thank you. So, the one that's up, sorry, she's like, I'm just writing, whatever. The one up at the top now, take a look at that one. I want you to see if you and your neighbors can do the continuity test for that one and see what you come up with, okay? Go for it. Step 1, find f of -3.
I found the answer. I think.
Step 2, see if the left and the right are the same. Step 3, see if step 1 and step 2 match.
What if they don't match?
If they don't match. If it fails the step, then it's discontinuous. For the first one, it does. Like, so for step 1, you're finding, like, pretending you're not doing a continuity test. If I would ask you to find f of -3, there's only one answer. You can't just pick which one to put it into. And in piecewise, you have to figure out which of these two, -3, is actually in the second one, because this is including. Okay, so you're gonna look into this one. For the second step, because we want to still look at both sides, we're gonna end up looking into both things.
I have a question. So, with this big jump,
Yeah, so the good thing with, like, when that happens, is that's kind of one of the cases where you can figure out the type of discontinuity without your calculator still. It's hard to tell with, like, removable and infinite until we look at the picture. Like in that one, there was no way for us to, like, really see what was going on, but the jump is, like, clear because you got two different values. Yeah.
It's 1 and 5.
In this one, yeah, 2 minus -3 is 5. Minus negative is plus. It's not right. You know which one?
yes.
Okay. So sometimes it's going to be a matter shell, and we're going to use graph as a strategy. But in this one, we actually can kind of already see what's going on without graphing it. Because if we think about it, it's 2 lines, right? One of them we know now is approaching what? 5, and one of them is approaching -7. And so you can already picture what's going on in your graph. It's going to jump. Okay? So like that one, it's kind of like, there's not like a clear picture. Sometimes you're going to be able to figure it out, and I can put a question like that on a non-calculator. But other times I'm going to do they need a calculator to talk about this and put it on a calculator. The whole test or just. Okay, so which type of discontinuity is coming from whether we're approaching infinity and negative infinity? That's infinite. It keeps going to infinity. Like we're talking about our y values, so our y values are either going up forever or down forever. Okay. If it's jump, it means our y value in one place it's coming up here to like 2, and another place it's down here like -5, and so it jumps from here to here. Okay? Removable means it's coming to the same place, but then right at that point, I removed it, I plucked it out, so there's like a little hole there. White hole. That means it's not there. But it could be like, it could be, I like that, but it could be a hole, it could be like replaced, it could be removed, and then like plopped right above. So the dark hole could be there, but like up higher. Yep, Zulema? You're going to problem set?
Yeah.
Okay, let me wrap up this one because then we're all actually going to go. This is the last example I have, so then we'll all turn there and like work on it. Cool? So just pause for me for 1 second. Yep. About this one? Just general, can we all hear your question? No? He's like, no. Yes? Okay, what's your question?
How do we know, what circle is open or what's not?
Gotcha. So if I give you a graph, it's going to be clear, right? If you graph it on your calculator, it's going to be a little more unclear, and so I'm going to show you how to use a tool called the trace tool, where you have like a little cursor that goes along and you can watch the points, and if the point is undefined, then that means it's not there and it's open, and if the point is like -3, 2, then it means they both exist and it would be like a closed circle. Okay? So we're going to do that on our calculator in a second when we look at the problem set. Okay, so this one right here, step 1, when you plug in -3 to the second one, did f of -3 exist? Did f of -3 exist, yes or no? Just like nodding or something. Yes. So step 1 we passed. Woo! Maybe it's continuous. All right, let's check step 2. Left and right side. When we plugged it into both of them, Cecilia, when you plugged it into both of them, did you get the same value, the same approach on the left side and the right? No. What were your 2 values? 5 and negative 11.
Negative 5.
It's 7.
Let's see. 3 times negative 3 minus 2 would be negative 9 minus 2 is negative 11. Cool. Because I did see some negative 7s out there, so I wanted to check. So this is negative 11, and that one was 5, and so we know automatically it failed that, so we know it's discontinuous. However, at that point, negative 3. However, I asked you what type, okay? And a lot of people had some good questions about how do I know what type. Visually, if you graph it, you could see probably that could give you some information about what type. But actually this one I should be able to give you on a non-calculator section, because just thinking about it and the fact that one of them is going to negative 11 and one of them is going to 5, we should be able to like picture kind of what's going on with our graph and say that it is, Jacqueline, what do you think? What type of discontinuity were you thinking? Jump. It just jumped from one value to another value, right? So this is jump. I know you can't really see it, but it's down here. Jump discontinuity at x equals negative 3. And I went ahead and graphed it on my calculator just to like check and prove it to you. And here we are coming into 5. Here we are coming into negative 11. And you can see that jump right there. But I could give this to you on a non-calc section, and you should be able to get enough information to figure that out. Okay? All right. Let's take a look at your problem set, some problems with our remaining time. So that way, as you look at them, there's going to be some things that you run into that you might need your calculator for. So I want to talk about some of the tools we have, like our trace tool on our calculator and all that stuff. Okay? So get your calculator out and get your problem set out and start taking a look. And then when we get a question, I'm going to kind of like bring us up here to talk about it. Yes, I'm going to answer your question.